So yeah, so we kind of stopped with SGD. So I thought we'll start from SGD. First part kind of dives into kind of an intuitive explanation, which I stole pretty much from FastAI. And then we'll kind of jump back to the named entity recognition that we were doing and see how SGD kind of plays along over there. So yeah, like I mentioned last time, anyone with questions, please jump in. Anyone with any corrections, any extra things to add, please feel free to jump in. Cool. Stochastic gradient descent, this is what the formula kind of looks like. And the bunch of things that are happening over here, I've kind of written them down, like the things that we need to cover here. What is the stochastic? What is gradient descent? What are parameters and activations? What is this step size LR? What is nabla gradient? And what is this J? So you kind of look at this formula when we kind of cover a bunch of next slides, and then I think everything should kind of make sense. So yeah, kind of let's look at what parameters and activations are. So parameters are something, basically these are the weights and biases of your model. And these are the things that once you run through a forward pass and when you're doing the back propagation, these are the things that you keep updating. And that is what kind of helps to improve your model through training. Sorry, is there a question? Oh, someone is not muted. If they can mute themselves, thanks. Cool. So activations are basically numbers that you calculate. So if you look at the model down, this is actually, yeah, stolen off FastAI. So these yellow boxes, this yellow box that I'm kind of currently pointing at is, if you remember, our equation was of the form Z is equal to WX plus B. This is what the W is. And this is what you would multiply your X into. So you would get your first set of activations, that is this. The B is not here, but you can just assume that they're all zeros for now. Otherwise, you would just be adding that B along with this. And you get your first set of activations. Kind of an important thing to remember is whenever you apply an activation, it really doesn't change the shape of your matrix or your vector because it's an element-wise operation that you're doing. Whereas when you're doing like a WX, because that's a matrix multiplication, so there is potential for you to keep changing the size of your matrices. Just a side point to keep that in mind. So you get this activation, you apply this ReLU, which is you're just doing max of 0, x. Like I said, it doesn't change the shape. And this is kind of the next layer or the hidden layer that you're kind of operating at, which is again like another W. And you can see this is an 8 by 5. You multiply it with this. Again, last time someone pointed out that this multiplication is not valid, but yeah, it's just taking the transpose, or otherwise you just put this over here to this side. And the matrix multiplication works. Again, you kind of get another set of, you've calculated these values, so this is another set of activations. You apply another ReLU. Again, you're calculating the next set of activations, go on with the next layer. And at the end of the day, you get this certain output. And to this output is where these are basically just activations, right? And now these activations have no specific nice properties to the numbers. It can be in any range. So that's what we previously discovered and discussed. What softmax does, why do you need a loss function? So all that kind of plays in together here. So you get this output. These numbers are not nice, so-called. So you apply like something like a softmax, or follow that by a negative log likelihood, which kind of gives you like cross entropy. We kind of discussed those terms last time. And this kind of gives you numbers, probabilities. So they're like in the range of 0 to 1. That's a nice property we would like. And then if you do an argmax on this, you're basically picking out, give me the position where you're getting the largest probability. And this basically it's 10 because you're kind of looking at MNIST data set. You basically have numbers 0 to 9. So you're trying to pick out which number or which image of the number was initially read in. And this is what the actual output is. So in terms of y hat and y, this would be kind of your y hat, your predicted value, and this is your y, which is your true label. You can take a difference between these two. We kind of go through that in the future, but basically this is what will give you your loss, which tells you how good or bad your initial sets of weights were in helping you predict the true value. And it's obviously the first iteration is going to be bad, so you get a bad loss. But now this is where kind of the whole magic of machine learning and deep learning kind of happens is you use that loss and you take the differential with respect to the weights and biases and you update it. Now, that is what we'll kind of look into next. Yeah, this is something we already discussed before. Yeah, so activations don't change the size of the matrices. Yeah, you calculate this loss, error, J, all these kind of similar terms here, and you're doing the gradient of the loss with respect to your parameters so that you can update them to minimize your loss kind of on the next iteration. So this J loss or error is what we spoke about on this side of the slide. You just take a difference, a bunch of other loss functions that we can discuss. Now kind of comes what the stochastic gradient descent is and what a gradient is. So let's say you have a curve which is of this form, and actually, hang on one second. Let's decide what is this gradient. In intuitive ways, if you know the equation of a line, y is equal to mx plus c, this m is basically what tells you what the slope of the line is. And this gradient is, again, kind of basically trying to find out the slope. And how you find out the slope is you take the derivative of this, and that's what you get. So if you take the derivative of this equation with respect to x, c is a constant, so it drops out. Dy by dx is basically mx is, if you take the differential with respect to x, that is m. Again, that is what the gradient is. That is what the derivative is. That's what the slope is. Yeah, so let's look at this. So yeah, if you're trying to find the slope of this line, kind of remember geometry, it's basically telling you the difference in y, that is this value for these 2 points corresponding with the difference in the x values, right? So that's what that is. M is rise by run, which is delta y by delta x. Here you can kind of define what this A is. So this is kind of your original point. So they're defining A in terms of this x. So it's x plus delta x. And B is again y plus delta y. And then you know that B is y is equal to f of x. So they kind of substitute that in and you get this. And the idea of this delta x is basically delta x is trying to show that delta x is tending to 0 basically means that this difference is really small. It's tending towards 0. And that's where kind of it moves from, what is it, like discrete values to continuous values. Again, that's pretty much what the slope of the gradient is. And if you put all that together, you get, this is your delta y, which is the change in the y divided by the change in the x. And this is what differential is. Yeah, so if f of x comma y comma z is basically of this form 3xy plus z square, and then if you take a differential of, the gradient of that, there are 3 variables here. You have x, y, and z. So you basically have to do them in 3 parts. So first you go ahead and differentiate with respect to x. So that's why you get 3y. That's the differential with respect to x. Next you differentiate this with respect to y. You get 3x. And then next you differentiate this with z. So you get 2z. So that was kind of like a quick refresher. Now kind of jumping into gradient descent. So this J of W is what we kind of discussed was our loss function of the error that we're getting. And that is what this kind of curve or bowl is. And now the idea is this is with respect to your current set of weights that you had chosen, weights and biases, or basically the parameters that you've chosen. This is what you got as the loss now. Now the idea is that you need to change these W somehow, that is the x-axis, change this W somehow so that your loss becomes the minimum. Now, how do you kind of go about doing that? That is where this gradient descent comes into picture. So again, kind of breaking these into two parts, there is gradient. So what is gradient? We already discussed that. That was kind of giving you the slope at a point. So you make an initial guess on this bowl or this loss function. So you choose a certain W. That is what, if you were trying to go back to that figure, it's like randomly chosen
Sorry,
W.
Prashant. So just a quick
Yep.
question to you.
Mm-hmm.
So you've got the JFW versus the weight. Now,
Mm-hmm.
if you're talking about the the example that you have where this is MNIST, and let's say this is your inner layer. So you started with 784 by
This one, right?
yeah. So let's say we're picking one of the inner layers. So let's say
Okay.
784 by, or say 8 by 5, right?
Okay.
What is, so if my let's say I'm picking this inner layer of 8 by 5,
Mm-hmm.
what is that when I plot JW by W?
Ah, okay. I see what your question is. Okay. So that W is basically all these yellow boxes. Does that kind of make sense? I think the disparity that you're having is right now is this is going to basically not have, this W is going to be like multidimensional, right? But what I'm trying to show you in that figure is just 2D in that sense. So it's basically only you're trying to change one set of weights. So this jumps into like, if you can, I think the next best you can draw is like in 3D where you have two sets of weights changing, and then the other axis would basically show you how the loss function varies.
Okay, fine. So then basically I imagine some sort of a plane, but
Yep.
if I have an 8 by 5, right? So the X
Mm-hmm.
and the so let's say the bottom and the one that's coming out is 8.
Mm-hmm.
Is it the case that when you say you've got an 8 by 5 matrix in that case, and so the one that's pointing up is your loss function, and so you've got a plane, but what exactly is that? Is my x-axis and y axis? Is it the 8 by 5? Is it one of the weights? I'm struggling to
Oh,
visualize
that way.
what that is.
If I'm not wrong, that is actually just one of the weights that you're trying to change. Actually, there's a better, we'll get into kind of the code that I have there, and there you'll be able to see how we change the weights. So yeah, that is basically just one of the weights that you're trying to show. So this has to happen kind of, or all the weights. So you're going to get like a multidimensional plane, I mean, a multidimensional loss function, right? And you're trying to find the minimum within that that loss
Okay.
function.
So in your diagram here, you've got 8 by 5, which is 40, right? But what you're saying is that diagram that
This
we,
one,
if the
right?
3D one, it would
Yes,
actually be just one of those 40.
yes, yes, yes.
Okay, thank you.
Cool. So yeah, so you make that initial. So yeah, so we need to somehow find out how do we mathematically kind of get, or tell your computer to kind of get to this minimum spot. So you can find the gradient, and basically that is the tangent at this point. And once you find the gradient, basically gradient is telling you, we discussed the slope, right? And in convention, anything which is, so slope is kind of measured from x-axis going anti-clockwise. So for this point, if you're looking at this point, if you look at this gradient, the slope is, it's positive. Let me actually rephrase that. So any line which is this, so this y with respect to x, this is a 90-degree slope, and tan 90 is not defined. So this slope is not defined. Anything in this quadrant, since you're measuring it this way, the slope is going to be positive. Anything that lies in this quadrant or is in this angle, the slope is going to be negative. And yeah, x along with the x-axis, the slope is 0 there. So now putting all that together, if you look at the slope for this line, it's going to be positive, right? And you know if the slope is positive, that's what the gradient actually tells you. And you need to know, and you know that if you go further ahead, your slope is just going to increase. So what you need to do is go backwards. And that is where this formula, this minus, comes into picture, right? And this delta loss with respect to delta gradient is, a delta W, this is what is your gradient. Now, imagine you were at this point, what would happen is your gradient is like this. And like I told you, the gradient, which is in this direction, is going to be basically a negative slope. So you have a negative slope. And now you know that if you move forward is where you're actually getting towards your minima. So that's why the minus of that minus will basically make it positive. So you're actually moving in the space of W, you're actually moving forward now. Does that kind of make sense? That's kind of the intuitive explanation for gradient descent. Anyone have any questions, or shall we proceed? Cool. Okay, so next is, what is this word stochastic doing over there? So this basically is, let's say you have like a ton of number of samples, you have 100,000 samples, and this is going to be just too memory intensive to put all this in your, sorry, so 10,000 samples. So you basically have to create like a weight matrix, which is going to be W on one dimension is going to be this, right? And if you have like multiple layers like that, the W's and the B's put together, the parameters are going to be like super huge. You do not want to do that. It's going to take a lot of time. So what you do is you deal with them in batches. So batches is basically you kind of break this down. Your the size, you just take like, let's say 100 for that matter. And yeah, just you randomly choose these 100 samples. And this is how you want to run your gradient descent and then update your parameters. So you take your, so this is where this word stochastic comes in. And the advantages of kind of doing this is, though it doesn't, obviously it's not going to give you the exact same answer as when you took the 100,000 samples. So this is kind of a approximation, but it's a really good approximation. And the biggest benefit is that it really makes things go super fast, because you don't have to wait for calculating the gradient on this huge dw by delta of loss by delta of the parameters, which is going to take a lot of time, whereas you're doing this at a much smaller scale. And once you finish this with the first batch, you randomly choose another set of samples, and then you kind of go back and update these parameters, and then you repeat this basically. One epoch would be going through all these batches, and then you can do multiple epochs after that. So this is faster, less memory intensive, and yeah, that's kind of the understanding behind what the stochastic does there. Cool. So yeah, this is kind of answering your question about W and kind of looking at what stochastic gradient does. This is kind of on a, it's a really smallest scale that you can think of. Again, copied off fast AI. So this is what you have, right? You have y is equal to ax plus b. So think of this as something like y is the number of bacteria that basically changes with x, which is your temperature. And you have these parameters a and b. So this is just a line. Kind of, you can rewrite this line because you want to do some matrix calculations, because that's what makes things fast. And you can parallelize it nicely. So let's add another term here called x2. So you have a1 into xi1 plus a2 into xi2. This a2 is nothing but this b, this a1 is nothing but this a, xi1 is nothing but this x, and xi2 is nothing but 1. So basically, you just reiterate in this y is equal to x plus b in terms of that. This kind of lets you now put this in the form of matrix equation, which is y is equal to x into a, where x is nothing but xi1, xi2, and a is a1, a2. These are your two parameters, a1 and a2, which is equivalent to w and b. So now we're kind of going to run through, you're going to simulate a data set where you already know what a1 and a2 is. And then you're going to pretend like you don't know what this a1 and a2 is, and use stochastic gradient to kind of guess what the a1 and a2 is. So that's the setup for this problem. So now first to create that, you basically say you have 100 samples, you grab in what, you're just setting this x2 to be all ones because that's what you want. Initializing x to be random values between -1 and 1. So this is what you look at the first 5 rows. This is what it looks like. Second column is basically all ones. Let's start with our actual parameters. This is what we're going to be trying to guess at the end of the day. This is something you don't know in real life. So A is 3 and 2. So this is basically A1 and A2. do a matrix multiplication between those two, add a little bit of random noise, plot that, and this is what you get, which makes sense because you're plotting y is equal to x plus b with a little bit of random noise. So now if you go back to this, we made an initial guess over here, right, for what is, which put us at a certain loss. So let's make that initial guess to be a is equal to -1 and 1. That's your initial guess. And we'll define something, our loss function here, to be MSE, which is mean squared error, which basically, let's break that down again. Let's start from backward. What is the error? So if this is the actual line, the blue one is the actual line, and the purple ones are the ones you're guessing. So the error is going to be this point minus this. So basically this distance is what your error is. So you can have all these errors. And now you're taking the square because you can see your errors are going to be positive and negatives. If you actually just sum them up, you're going to kind of cancel out each other, which is not what you want to do. So that's the reason why you do a square over there. You take the square, so then you get the square of the errors, and you have all of them now. So I mean, you want to take an average of all of them. So that's what the mean comes in. So you square all the errors, add them up, divide the number of samples. You have probably seen root mean squared error because now you took the square, you are kind of in a different range. So that's why you kind of take the root to kind of bring it back in the range of these data points. So that's the error we are going to use. So define that. Y hat is basically your predicted value. Y is your actual value. And all you're trying to do is do y hat minus y, take the square of that, and take the mean of that. So now you know your initial A, you made your initial guess for A. So let's take that A, multiply it with X that you have, and let's see what the mean squared error on that is. You'll get something like 8. And if you plot that out, this was the original data, that is the Y, and this is kind of the Y hat that you're going to be the orange line. So now the idea is you want to predict these A's in such a way that this orange line kind of coincides with this blue. So let's make a few guesses. Like we started with -1 and 1. Let's make a guess of 1 and 1, 3 and 2. And it so happens we know that 3 and 2 is the right one, and that's what this one is. But the question is, you don't want to you don't want to guess this, right? You want it to kind of happen in an automatic fashion, and that's where, yeah, this kind of this is where I kind of wrote this back in Torch. Getting to this point, yeah, this is where all the magic kind of happens. So these are the steps. You take X, you multiply it with whatever your initial guess is. You calculate what your loss function is. This kind of tells you how bad your initial weights and the weights and biases, the parameters are. You do a loss dot backward. This is what is basically calculating the gradients of the loss with respect to your parameters. This lets you kind of go back and update your weights and biases so that on your next iteration, you should probably get a better answer, which is a lower loss. And this is what the gradient descent equation is like, how you update your parameters. So you have A is basically your old parameters. This A on the right-hand side is your updated or the new parameters. A dot grad is basically giving you the gradient, and LR we'll again look at is basically what is your learning rate or what is your step size. So you run this, you chuck this into a function, this is what you get, and you run this, let's say, for 100 iterations. And the key thing to look at this is on the left-hand side of this, look at this, I'm actually, where is that? Yeah, I'm printing out A and loss, right, for every 10 iterations. So look at the A. The A was our initial guess was -1 and 1. It started moving, and it started approaching to what we wanted, which is 3 and 2. Right, you run this for some more iterations, and that should kind of get you there. So that's kind of the idea of how the A is moving. And on the other hand, we know the loss, that if A gets better and better to the original values, that means your loss should decrease. And if you start looking at the losses, you can see the first one is 1.4, 0.4, 0.2, and then you kind of stagnate at 0.08. But you can kind of see that the loss is reducing over there. And yeah, that's what kind of gives you a perfect fit. Like I'm just using these last two A values that I get back. So I'm doing Y hat is equal to X into A, and this is what you get. So does that kind of make sense? Any questions over there? Cool, let's kind of move back. We still have to discuss what Wait, I kind of jumped something, I think.
So yeah, just on that. So
Mhm.
just like you've got the loss function with respect to the weight, I'm assuming
Mhm.
that you'd also have the loss function with respect to the bias, and you'd have a similar sort of diagram, or
Right, right. So that's what. So you won't be doing this as single diagrams, right? Because these all interact together. So you'll create another. So let's say if you were to add another W, so that would be, which can be actually another parameter, which is just, let's say, a base, a bias or a weight. This would become 3D. So now instead of just changing W, which is you're just moving in one direction, you would have one more axis coming out over here, right? So then you have this whole plane where you can traverse to find what is your best W. Does that kind of make sense?
yeah. So on your x-axis would be the weight. What would be the one that's coming out?
So you have three axes. You'll have X,
Yeah,
you'll have Y,
yeah,
and we'll call this to be Z now.
yeah.
So X and Y are basically two sets of weights. So let's say your model just had two weights that you needed to update. So if two weights are there, you basically have a whole plane to traverse to find the best weight. And if you have three weights, then you basically have like something like three dimensions that you need to traverse to find what your best sets of weights are. It's kind of hard to visualize that part of it. That's why this is the most easiest way to kind of understand, and it happens to work when you extrapolate it to many dimensions.
Okay, great. Thank you.
I'll share one more link which actually shows it in two dimensions. When I finish this, maybe that'll kind of help understand this a little better. So we kind of jumped over actually what step size or the learning rate is. So this is kind of a really important hyperparameter that you would have to tune in your models. And this basically tells you is once you find out what this gradient is, question is how much do you move by to find your next loss. So this update, if you update, let's say if your A is just too big, which is then you kind of overshoot and you reach somewhere here, which is you don't want to kind of you could actually traverse and find the way like this and then zigzag down and then get to this point finally. But ideally what you would like to do is take decent amount step sizes so that you traverse kind of down like this and then you fall into this smaller region. You don't want it to be too small because then it's going to take super long. It's going to take a lot more iterations to kind of get there. So that's kind of the negative effects of taking a small step size. In general, I would say that taking a smaller step size, at least you will reach convergence. It may take too long, but if you make it too big a step size, then you can probably just diverge and just get out of this loss function altogether. The other thing is, as you kind of move down this loss function and your gradients, you're using your step size. Ideally, what you would like to do is you would like to take big step sizes as you go and then kind of make them smaller and smaller as you're kind of reaching your minimum point. And that's what is kind of called annealing, which is as you go down, you kind of automatically reduce the step size. So, yep.
So just one more question around this diagram.
Mhm.
So is your, when you're taking the loss with respect to the weight, that bit
Mhm.
that you've got circled in purple,
Mhm.
is there anything really clever going on there, or is that basically just a flag to tell you whether you should move left or right, and so changing the sign of that minus in front of it?
No, that's a good point. Actually, yeah, so I think it's kind of tells you this gradient, right? The gradient is the one
Yeah,
which is like telling you whether if it's sloped like this, then it's a positive slope. So like you said, you don't want to change the sign, you want to go backwards in W. Whereas if it's on this side, then your slope is negative, so that becomes negative of negative, which is telling you that you need to go forwards. So
right.
it's pretty much, yeah, you can kind of think of it like a flag. Uh, Anything else?
Okay,
Or
no,
shall
that's good. Thank you.
Okay, cool. Let's proceed then. Yeah, I just wanted to kind of this, though they use WW over here, it's like this is WT, which is otherwise represented here as theta nu. Where is that? Yeah, theta new and theta old. So that's what this is on your updated This is your updated iteration where you're taking your kind of from the previous iteration and you're updating it with these values. So yeah, kind of getting back to this. So that's kind of looking at it in like y is equal to mx plus c, kind of the simple form. Now we have a lot more inputs. You have x1, x2, all the way to xn, which is kind of like a, yeah, a vector of inputs. And kind of the difference is like there is a you take a derivative and there is something like a partial derivative. So partial derivatives come into play when you're basically having multiple inputs, changing the output. So you can't take like a derivative. Again, I really don't think there's much of a difference between these two for us. So though the symbol is kind of different, this becomes like dou of f by dou of x. This actually is nothing but you can just take like the full derivative of f with respect to x1, f with respect to x2, and so on and so forth, and you'll basically get a vector of these. This is again, so you have all these terms which are there. You have gradient, you have derivatives, you have partial derivatives. Then there is something called Jacobians. Jacobians is again like a partial derivative when it comes for a matrix. Again, it's the same thing. You can pretty much take the derivative for each of these with respect to f with respect to each of these inputs. So that's what you kind of get here. Yeah, the other important thing with backpropagation now is chain rule. This z, actually think of it as written as z is equal to 3 times x squared. And now you can split that out as z is equal to 3 times y, and y is equal to y is equal to x squared. So you combine that back up and you basically get back your original function. So the chain rule basically is telling you that you can treat these parts as take individual derivatives and just multiply them up together. So if you're doing dz with respect to dx, all you need to do is dz by dy, dy by dx. Dz by dy is this first part, dy by dx is the second part. And if you kind of look at it, if you can't, but you think of it like you can cancel out this dy and dy, you get back dz by dx. So that's what you're kind of calculating. So for it to work out, dz by dy gives you 3, that's what you get here. Dy by dx gives you 2x, that's what you get. And I told you the original function was, you can imagine that to be as 3x squared. So if you take 3x squared and differentiate it with respect to x, you get 3 times 2 times x, which is exactly what you got here. So that's what the chain rule is. And how does the chain rule kind of play along with this diagram? That is because these are all a bunch of multiplications that happen, right? Just kind of keep that diagram in mind. And yeah, let's look at this. So you had initially this x, you multiplied that with this w, and you added this b. So this was like kind of your first step in this part, right? So you got this. Then you kind of passed it through an activation function. Then you kind of pass it through another w and b. So you get another, so you get like these multiple layers, you're kind of multiplying them all together. So instead of kind of doing that whole differential in one step, what you can do is the chain rule is telling you that take the differential of this, take the differential of this, take the differential of the next layer where you're multiplying by w and b, and then individually kind of multiply them all together to get your differential of the loss with respect to your inputs. So that's why the chain rule kind of plays along with the oh yeah, correct. This is the other thing I wanted to kind of mention, that though it's written here, you're differentiating with respect to x. X is your input. You in reality, you really don't want to be changing your input. What you're differentiating with respect to is w and b, and you're taking the differential of the loss with respect to w and b. Yep. Okay. So yeah, here also again there are a couple of things in this slide which are written, which actually note what we do. You're taking here, he's trying to take the differential of s with respect to b. Here again, you don't want to be taking the differential of s. You actually are taking the differential of the loss with respect to the weights and biases. But just kind of in your head, kind of try to replace this s with the loss. So we went through this last time where this was kind of the setup for NER. And what you were trying to do was given x, which was inputs, basically you have these words, you kind of grab They're word vectors. Those word vectors were like, we said that there'll be like 40 vectors and we'll concatenate them. So you get this 20 cross 1 thing, which is your input. You take that, multiply it by W, add the B, so you get the intermediate step. Then we discussed about why you need to pass that through a nonlinearity, which was our F, which is kind of what really helps the machine learning to kind of do the curve fitting part of it, so that you get nonlinear boundaries. So you get this, and then you multiply that along with U transpose T, which basically is like a dot product. So you finally get back a single value at the end of the day. So now, again, putting all these things together of chain rule, the trick about how we split this 3x squared into two different functions. That's what here also he's trying to do that, where you have this activation function, which is basically you're composing two functions here. You're doing wx plus b, and you're passing that through an f. So he breaks that into two functions where z is basically wx plus b, and you're passing that into the activation function. So now this kind of gets split up into two parts. The other thing with differentials is like, differentials is kind of complicated in the sense when it comes to multiplications, divisions. When it's an addition, you basically are just you're basically adding on that differential to it. So that pretty much can be put in all in one step. So all your additions and subtractions can basically try to stay in the same step. You usually want to move your multiplications into kind of different steps and then perform a chain rule on that. So this is what it was, right? X, you passed it, you got Z, you got H, and then finally you get back this S. And this is, if you were to take the differentials, this is what you would get. And now you want to do ds by, we are doing with respect to the bias. And if you follow the chain rule, ds by db is basically ds by dh. That's what you get here. And then h with respect to z, and then z with respect to b. Now, ds by dh, we can use this, which is basically, again, the transpose, you can kind of look into it, but intuitively it's kind of doing something like d by dx, d by du of, let's say, u into h. And if you were to treat kind of the u, let's say u is something like x and h is like 2. So basically you're trying to do d by dx of 2x, which is going to be nothing but 2. So that's how I kind of imagine that to be. And we kind of get into something like what he discusses later called shape convention, which is kind of a way to kind of guess what this, whether you need this transpose or not, or what the shape of these edges should be. Next was this f of z. F of z basically was the activation function, and something that we discussed previously is that activation functions really don't change the shape. So, and it's going to be it's going to work element-wise. And that kind of gives you this diagonal of f dash z. And d by dp of wx plus b. Wx is not a function of b, so that goes off. D by db is like 1. But then again, because of the shape convention, you want your gradient to be of something of the shape of what this would be. And the shape of this is basically the shape of w times x. So your identity is going to be the shape of w times x. So you put all that together, you get u transpose diagonal of f dash of z into I. This kind of is nothing but multiplying it into identity. So this gives you back diagonal, f dash of z. Hang on 1 second. Let me actually jump over to, yeah, okay. I thought I'd written it down. So yeah, so you get, this is nothing but diagonal of f dash of z, the identity goes away. Now, how does this kind of become this u transpose into f dash of z, where this into is basically Hadamard? And Hadamard is basically nothing but you're doing like an element-wise product. So something to keep in mind is that the shape of this is not, you're not going to follow the conventional matrix rules. It's not going to be like m cross n into n cross p, which will give you n cross p. This preserves the size. You're doing an element-wise product, so it kind of preserves the size over there. So looking at this example again over here, I've kind of written down the 8 cross 20 gets multiplied to 20 cross 1. You add in the bias, you get your activations, and finally you get this u transpose A, which gives you this single vector. And this U transpose into diagonal of f dash z. This is what I've kind of done over here. The diagonal of f dash z is what looks like this. You have only elements on the diagonal. The others are 0. So imagine if you have this to be 1, 3, 0, 1, and you have some diagonal values here. So you take this row, multiply it into this column. Effectively, you're just multiplying out the first element in this with the first element in this. Take that, multiply it into the second column, and that effectively is just multiplying the second element into the second element of the second column. So that's why you're doing this element-wise product, and that's what kind of makes sense. So this is kind of like a small example that I kind of drew out to explain it to myself. And that's why that's kind of how you end up with U transpose times f dash of z. Hadamard element-wise product with f dash of z. So does that kind of make sense? Are there any questions on that? No.
Okay. Prashant, sorry, hi. Yeah, hi. The thing is, in regards to the partial differentiation of h with respect to z, so you're getting all the diagonal elements and giving it to be f dash z. Can you kindly provide an example? I mean, how does that just give the diagonal elements to be true?
So you want to see how that? Right. Okay. Let me just quickly pull up that slide. Where is that? Okay, here it is. So, right, so you want to see what dH by dz is. So, okay, so h basically is activation function applied on this z, and this happens to be, in this case, you're having z is going to be just a row vector of size, a vector of size n. Now the thing is, when you do dH by dz, what is happening over here is, for each element of I, you're trying to take the differential with respect to z, right? And this differential is going to make sense only when the z happens to be I. Z and I are basically the same thing. If z and I are not the same thing, there is no differential to be taken over there.
Yeah, I mean, sorry. Sorry. My question was, since I know the differentiation and how it will be I equal to z and stuff. So
Okay.
I'll reframe my question. So, you said like h should be a row vector, right, of size n, and h was the activation function. So since we all know, there are several activation functions like 10h, or you take it value. So in that case, suppose h, so do you mean like f of z would be equal to e power exponential power x minus e power minus x? That's the equation by e power x plus e power minus x. That's the equation for tan h activation function. Are we differentiating with this on that? Or how what is f of z? So f of z can be real or it can be sigmoid. So
right.
Would that
so let's take this to be like ReLU. So ReLU, is basically nothing but max of 0, x, right? So if you want to take, right, so if you want to take the differential of that, let's first split that ReLU into two parts, right? So you can write that ReLU as, if x is greater than 0, your output is going to be x. And if x is less than 0, your output is going to be 0. So now you basically want to differentiate these two parts. So the bottom part, which we said, if x is less than 0, output is 0, differentiating that doesn't do anything. You're going to get back 0. And the numerator, not the numerator, the top part where we said, if x is greater than 0, you're getting back x. So the differential of x with respect to x is nothing but 1. So that is what that differential is. Now, with respect to tan, if you're doing the tan h, you again do it the same way. Yeah. And then for each element, you would apply that differential. Does that make sense?
Yeah, definitely. That makes sense. So I was just wondering, with tan h, since the equation is exponential, it would be, quite a long and
I can't remember at the top of my head. Tan hyperbolic already has like a standard derived, right? So you will get, let us say, for example, I'm just saying, for example, let's say it was sine. So instead of tan, you're using like a sin x. So sin x differential, you would use like a cos x. So you just basically take
Cos
that
x,
activation, pass it through cos, and that would be your output.
Okay. Perfect. Okay. Thank you so much. Yeah.
Cool. All right. So we kind of finished that. Sorry. Okay. Cool. So we kind of discussed about how you would need to take the differential of the loss with respect to the parameters. So that's what it was with respect to dW and with respect to dB. And when you calculate these two with the chain rule, you kind of realize that the first part, the part in blue, is basically identical. So you want to avoid doing these duplicate computations. So to kind of do that, you kind of store, to kind of understand why these two are identical, he goes ahead to explain that this W and B actually play a role only at this level, but you're taking X, multiplying it with W and adding in B, so that is at this level. After that, all the operations that you do, that is taking the activation function, multiplying it by U transpose, basically all that is the same, right? So that is what is kind of why this part is the same, and only the difference is with respect to the W and the B at this level. And this common part is kind of the local error signal, which he calls delta, which is the computations of the neural network above this W and B. So that is kind of introducing that new thing, which is the error signal, which is called delta. And so using this equation of delta S by delta W, replacing this by delta, you kind of get this this delta and this both again, you have the overload in notation over here. This is kind of the differential sign. This is the delta sign, which is for the error over here. So we call this dou S by dou W is delta times dz by dw. Same thing, you can substitute that in over here. Dz by dB we knew was identity, so this kind of gets replaced by nothing but delta. And so this delta was ds by dh into dh by dz, and using these formulas, we kind of showed that it was the Hadamard product of U transpose and f dash of z. What else is there over here? Yeah, that's kind of basically, so if in essence, if you calculate this delta once, it should be more than enough to calculate for both these, which is making your partial derivatives faster. You're reusing that. You're not calculating things twice. So that's what the error signal thing was. Next, getting into shape convention. So if you look at this, this is where the gradient is, right? So taking the gradient of J with respect to theta, or otherwise loss in terms with respect to your parameters, you kind of actually want something to be the shape of this theta old. Then you can have basically like two matrices, and you're just doing like matrix subtraction. So that is what the shape convention is. When you actually do this derivative, there are a bunch of ways to take this derivative, which can basically give you a shape of a 1 by m cross n, which is not what you want, because then you'll basically have a matrix minus a vector, and that just doesn't make things easy. So that's why you want to somehow calculate this derivative in terms of a matrix in the size of this matrix. So then you can just do normal matrix subtraction. That's where, that's what shape convention derivatives with respect, in terms of the shape convention is. And that is, you kind of, again, you do the Jacobian and you kind of try to preserve the shape. That is what I understood with that part. So kind of getting into ds by dw, looking into that more, we got that to be the error signal into dz by dw. And now you want to find out what this dz by dw is. And we know z is nothing but wx plus wb. So if you take the differential of this, again, with respect to w, b is a constant that gets zeroed out. So you have wx with respect to w, which you basically need x. Now the question is, how did this x kind of become this x transpose? And this is where it's kind of an easy way to remember. You need to preserve this shape convention idea. And like I said, this ds by dw was n cross m, right? So you want something to be the shape. At the end of the day, you want the ds by dw's output to also have the same shape as n cross m. And the only way to kind of get that is you have delta, which you know is n numbers, and you have x, which you know is m numbers. And now if you're given n numbers and m numbers, how do you get n cross m? You basically have to take an outer product. So that's what this delta t becomes n cross 1, and x transpose again becomes 1 cross m, which take the outer product, and that gives you n cross m. That's kind of the hacky way of doing it in terms of preserving the shape convention. And yeah, this is kind of just explaining out the same thing, how this kind of becomes delta transpose and x transpose. So if you look at this, you have zi, wij, and xj. You take this xj, which is passed into wij multiplied, and you get back zi. So two variables here, I and j. If you look at this diagram, what those notate is W23 is basically the 2. The first index is which is your output, which is H2. And this 3 is basically which is your input, which is X3. So this W23, if you map that out like to Wij, so you can see that I is equal to 2 and the j is equal to 3. I in this W matrix is going to be each row. So I varies like 0, 0th row, first row going down, j is for each column. And your x over here that you're taking is basically a column. So if you take this first row for matrix multiplication, you go row into this column. And that is where you kind of get this multiplication out where is that? Oh, here. So you're finding out tau of wj with respect to this z, where z is wix plus bi. And he's breaking them down out for, let's do it with respect to each I, so like each row. So wij with this differential, because there's no w term in that, that becomes 0. This x now can be rewritten as, because this x is actually a vector here, he's writing them down in terms of elements. That is what this, you have k elements in that running from k is equal to 0 to d, or k is equal to 1 to d. Okay, that should be d minus 1. So then you're doing wik times xk, right? So that is basically taking each element, multiplying it with that. So that is basically how you would write out like the innermost loop of matrix multiplication. So that's what that is. Now for this to make sense, I've kind of written that down here. And so let's say you're looking at the 0th row, and the 0th row, let's say, had some values like x, y, and z. And this column basically had values like 1, 2, and 3. So you do a multiplication on that, you'll get back x plus 2y plus 3z, right? And then you're doing a differential with respect to w 0 comma j. And 0 comma j is basically, j is varying 0, 1, 2. When j is equal to 0, you're differentiating with respect to x. J is equal to 1, you're differentiating with respect to y. When j is 2, you're differentiating with respect to z. So when j is equal to z, that is basically you're taking, I mean, j is equal to 0, you're actually taking out the x, right? And you're trying to differentiate this product with respect to x. And that's why you get back, these two are constants, nothing happens. I mean, not constants, they have no x terms, so that's why they get dropped out, and dx by dx basically is 1. This kind of shows that this is nothing but picking out k when it's equal to j. And that is why when you multiply these two and take the differential, it's basically like picking out when k, that jth value. So that's how I kind of understood that. And so this is like a single element. If you apply that for this whole row, you take with respect to y, with respect to z, you get this m cross 1 matrix. I mean, m cross 1 vector. We kind of discussed how you get this element-wise Hadamard product for delta. And delta actually, if you multiply these two 1 cross n into n cross n element-wise, you get back 1 cross n. Now going back to shape convention, you know w was n cross m. So you want delta of s with respect to delta of w to also be n cross m. So again, what I previously said, given n and m elements, how do you kind of get back that size? You basically do an outer product of these shapes. So this is what it's kind of like an intuitive way of kind of understanding things mathematically. I think if someone has a math background out there, it's probably not the right way of doing it, but just kind of helps you understand stuff. So that's kind of all that I had to cover for today. Are there any questions?
No, but thank you. You did a fabulous job. Appreciate your time.
Thank you. Anyone else have any other questions from last week's lecture that we covered? There was quite a bit of math, but I think, yeah, if you kind of go through these slides, and I think the most important thing that I find helpful is when you do all these matrix multiplications, vector with vector, always kind of keep looking at the shapes. And if the shapes kind of add up the way they're supposed to add up, that kind of already solves like half the problem. So I think that's kind of the real important takeaway for me. Cool. So if there's nothing else,
Prashant.
Yeah. Go ahead.
Yeah, hi. Thank you for the presentation. I mean, it was really clarified and it was really intuitive. I just had one small question with respect to the last time we discussed. So there was a formulae. I think it was something relevant to max margin loss, where 1 minus max of, if I remember correctly, it was 1 minus S plus SC.
You're talking of this one?
It was. Yeah, exactly. Yeah, right. So
yeah, I tried playing around with this. Yeah, I tried experimenting around with this, but yeah, I was not able to kind of get an intuitive understanding of what was actually happening over there. Does anyone else have a better idea of what was going on here that they want to chip in with? Yeah, I mean, let's discuss then. Let's see what your question is. Maybe something comes up with that. Go ahead, Sagar.
Okay, I was trying to implement this using, I mean, with the analogy of having a ReLU. I mean, how did ReLU came from sigmoid? So if you see like the sigmoid, initially we used to use the function of 1 by e plus minus x, 1 by 1 plus e power minus x exponential.
Right.
Then what we did was we wanted, since it was delimiting us from a range of 0 to 1, we wanted to play around more. That's how we evolved to 10H, and then ReLU came into picture because we wanted some linear gradient, and so that we can use differential rather than having a curved surface. And so I was just trying, I mean, using the
just to kind of clarify some of the statements you were making is ReLU and if you're talking of the sigmoid function, they both kind of play the same role of introducing nonlinearities. And I don't think one is derived from the other. They're both kind of individual nonlinear functions, and it so happens that initially sigmoid was something. Right. Okay.
Yeah. Go ahead.
So I was just going to say that sigmoid was something that was initially used in the literature, and then of late people have been using ReLU and leaky ReLU. So they both kind of do the same thing. It's just that of late, empirically, I guess, people figured out that ReLU and leaky ReLU kind of do a much better job than the sigmoid as such. Sigmoid, tanh, in theory, you can actually put in any nonlinearity here. You can probably put in a sine, put in a cos, in theory. That's what, yeah, just wanted to kind of clarify that. Yeah, go ahead.
Yeah, so sorry. Yeah, I understand that, but the point is, I mean, using sigmoid. So I mean, these days people have seen considerable improvement. As far my understanding goes, it's because the way ReLU works. I mean, the equation, it's quite linear in nature. So I mean, if you're trying to code that, and when the code runs, it doesn't take much of a time, right? Mm-hmm. Compared to that, if you're trying coding and using a sigmoid function as an output. I think something like this is covered in lecture 4, if I'm not wrong, if my memory serves well. But then I was just playing around with this, understanding the history of, I mean, how did this evolve into coming to ReLU? So I was just curious. I mean, I don't know. This may be the case. Like this equation quite resembles the equation of ReLU, where 1 minus S plus SC it's kind of the x of ReLU. I mean, where if the function has, so if you draw the curve, right, it's similar to ReLU. If the function is greater than 1 or something like that, it would have the value of 1 minus SC, max of that, until 1 minus S of A plus SC is negative.
Right.
So I'm not too sure whether I'm correct in that or not, but that was my analogy. I just wanted to get a word out and see if I'm thinking the right direction or it's wrong.
Yeah, unfortunately, yeah, I was trying to implement that. So basically, this was kind of used where if Paris were to be in the middle, ideally, this was kind of the loss function, right? So the loss function at the end of the day, what you want the loss function to tell you is if you're getting or predicting the right thing, your loss should be low. If you're not predicting the right thing, then your loss should be right? So this was kind of what I was trying to simulate, where these dashes are 2 words before, 2 words after, Paris in the middle. And can you remind me what S was? I kind of forgot what S was. Oh, S is basically the final output guessing, right? Okay. So S was that final, yeah, which basically tells you whether it's in the center or not in the center. What was SC? I don't remember what SC was. Do you remember what SC was?
Yes. Unfortunately, I forgot.
Yeah, I also can't remember.
See.
Yeah. I mean, yeah. Basically, I was able to kind of see that when you have
Sorry.
Go ahead.
Yeah, I think it was something relevant to the predicted model. I mean, so this was the expected output, right? And another one was the predicted one. So SC may be relevant to that. I'm not too sure. My memory is not serving well. So
the score of that class, yeah, I'm also not sure exactly.
Score of that. Anyways, please go ahead.
Yeah, so now I was just able to see for the first example. So if Paris were in the center, you want your loss to be low, right? So that's what I basically did. Like if you were to predict 10, and I don't know why I put class to be 1, and then I ended up with loss equal to 0, which makes sense because it's the correct prediction and you're predicting with a good confidence, so you want the loss to be 0. And I tried to implement that with if Paris were not in the center, your loss, you'll get a low output, right? Because that's what you're expecting your model to do. And your class is high, so you get a high loss. These two kind of made sense. But then when I changed it around, I don't know why I did this. Yeah, I can't remember. Let me try this. Let me look at this again.
Okay, no worries.
If I find something next time, I'll tell you.
Yeah, okay, no problem. Thank you so much. Thank you so much, man. Yeah. And this one thing, this presentation, have you put it? I mean, I couldn't find the link of this. I mean, is it somewhere?
The whole thing is there. I added a few more slides this time. I'll convert that to a PDF and I'll upload it up again.
Oh, please. Thank you so much. Thank you so much.
Yeah, sure. This collab notebook, I think I shared yeah, I can share the IPy notebook for this, and it's the same thing. I think it's lesson 2 from the FastAI DL1 2019 course. I mean, Jeremy's kind of gone over that a couple of other times also. Yeah, I'll share that also. Cool. So if there are no more questions, then I guess, are we done?
Thanks a lot, Prashant. It was a very good session.
Absolutely. I just want to kind of discuss, like, what is it that you guys are looking forward to do next week? Do we want to look at the assignment?
Assignment, yeah. I think assignment is a good thing to do, because if we move again to the further sessions, we may not again get back to the assignment.
Right. So the assignment, yeah, there are some of the, I think there's a good amount of doing these differentials, which I don't think I am interested in doing. But yeah, I forgot, like, for everyone who's still here, all these things are, these differentials are things that you are not going to be doing. Once you use PyTorch or TensorFlow, you're just going to be doing, like, the function, like when you looked at the collab notebook, you're basically going to just call like loss.backward, and that's pretty much going to calculate all the differentials and everything for you. So I don't see us really using calculating the differentials, so I really don't want to get into that part. I think the other thing that he wants us to do in the homework is kind of implement word2vec. And that I think is good value, because if you want to understand word2vec completely, it'll be really nice to implement that. So I am suggesting we at least focus really on that part. If someone else wants to cover the differentials part, totally go ahead. And the next lecture, I think the first 20-25 minutes is again kind of wrapping up the back propagation stuff. So I'm thinking maybe next week, if we can try to target at least some part of the assignment and the first 25 minutes of the next lecture. And does that sound reasonable?
Yeah, Prashant. Yeah, that sounds good to me. So we'll see also if more people chip in and contribute either in hosting or walking us through the assignments. That would be great. So we'll see. We'll post it in the channel, and if anyone is willing to take up the math part, maybe they can contribute in the next session. Or else we can, as you said, we can take up the word2vec part and the first half of the lecture 4. That sounds good to me.
Yeah, first 25 minutes. Then he kind of moves into like computation graphs, and I think we can do that like
Sure.
the next part.
Yeah.
Cool. So if there are no more questions, then I think we can wrap up today's session.
Yeah. Thanks again, Prashant, and thanks
absolutely.
Everyone for being here, and see you all next week. Bye.
All right.